Hello students. So in this lecture I will explain few problems based on your factor of safety and your theory of failure. Okay, so let's look at the first problem. Look at this. An offset link subjected to a force of 25 kilonewton is shown in figure. So this is the offset link. Okay, offset links are those where forces are not applied along its axis but away from the axis, either up, parallel to the axis but not along the axis. Okay, so this is its axis, so just applied above or below, anywhere. So this is offset link. Okay, so it is made of gray cast iron, the material is given, and the factor of safety is 3. Determine the dimensions of cross sections of the link. Okay, so for these type of problems you have to look at the figure, okay, and you have to analyze it, what type of forces have been applied, okay, and what type of failure is possible in this case. Okay, now let's quickly look at the type of failure possible here. Alright, so I'll show you this thing. Okay, pay attention please. So this is the 3-dimensional figure of your offset link. You understand? So here we are pulling along this line and at these 2 points. Okay, so its cross section, this is the cross section, right? This is the cross section, right? All of you know this is the cross section. So its cross section is given as, this height is given as 2 times t. Okay, and this is t. This is from here to here, this small thing. Okay, this part is t and this part is twice t. Okay, t is the thickness, you can see, right? So you know the cross section of this. So now let's quickly look at how it will fail. You see, anything, let's say this object, okay, or the metal machine part or something which is being pulled along the axis, this is the axis or the middle line, you can say, there won't be any bending in this case. Okay, because we are not applying any moment to bend this thing, there will be only tensile failure here. So after pulling, if it cannot take this load, whatever load you apply, P, so this will break here. Okay, one part breaks, another part will break here, they will separate like this. Okay, so all of you know this. But if we just apply a load which is not along the axis, okay, rather maybe let's say just the same object, okay, is having a cross section like this. This is what we have here. Okay, something like this. You understand? Okay, this has been modified and here we are applying a load like this. Okay, so it may break here. Okay, that is one possibility. Then it will be separated like this. Okay. Sorry. Okay, these are the separated areas. You understand? Okay, one possibility. Another possibility is, since it is not applied, the load is not applied along the axis is here. Okay, or you can say the connection where the axis, I can say here the connection is possible. Okay, so it is kind of, we are applying a load which is away from the connection like this. So it is obvious thing, just look at this figure and you will understand that it is going to bend the whole thing in this manner. Okay, if it is not breaking like this, then there is a possibility of bending the whole thing like this, isn't it? Right, isn't it? This is what you'll get, because they are pulling along with using the force, right? So this is the bending. bending failure, and this is your tensile failure. Why tensile? Because your failure area here is what? Perpendicular to the force. This is the direction of the force, right? This is the direction, or this is the direction. So your area is perpendicular to the force. So this is the tensile failure. Alright. So here this is a bending failure, because I mean if it bends like this, and ultimately it may break, it will start shearing from this point and it will break here. So this is not because of your tensile. Okay, so this is due to bending. So here maximum tension will be tension is experienced, and here at this surface maximum compression is experienced, and in between them there is a axis called neutral axis. All these things are from strength of material concept. Okay, now this thing you always remember, you have to take care of, you have to look at the figure. Okay, how it will fail. Now look at your figure. So there's again two possibility. One possibility is tensile failure. Okay, tensile. If it breaks like this, at that area itself, where it is this area here, right? So this can break it here, isn't it? This is the failure area now. Okay, this area is nothing but 2t into t. You agree? Because this is twice t and this is t. Okay, so these are the forces that we are applying, P and P. Okay, fine. So this is your tensile failure. Another failure possible is bending. So this is the bending type of failure. Okay, you agree? Because of pulling it like this, there will be some bending will take place. Alright, so here we don't take a failure area because it is still bending, it will break somewhere. Okay, rather we have to find out its bending moment. See, bending is caused by a moment that is called bending moment, MB. Okay, when we multiply in that case actually the area which is affected by bending, you have to consider that area. Okay, so this is the area, but we don't take the area exactly. Okay, we have to look at the area actually. Previously look at this. Actually this is not the proper way. So area will be bent like this. Okay, in this direction it has bent in this direction. Also here also, if you consider, area will be bent. I mean it is tilted actually, not bent. We do not call it a bending. Area will change its orientation either in this direction. Okay, any area you take. Okay, this is the same area throughout. Okay, now look at this. So into y bar, this is your centroidal distance. Okay, centroidal distance along vertical direction. Okay, so bending, see, the concept of bending that you have learned in your strength of material is important. Okay, so suppose there is a cantilever beam like this. Okay, cantilever beam here, and if you apply a load like this, then your beam will bend in this manner. Okay, then you always have to look, because your load is vertical here. Okay, and here also it is kind of, I mean beam has initially was like this, then it has bent in this manner. So you have to look at this cross section. Okay, or I mean how will I say this one? Okay, this direction, this is vertical direction because your load is vertical, or you can say it is going down or up along this plane. Okay, let's say this is x-axis, this is y-axis. Okay, so you can say in this direction this bend. Here also it is the same thing like this. So going vertically down, here also going vertically down. Or also you can say that initially the area was vertical exactly, now it has rotated or tilted along this direction or this direction. Okay, that way actually you have to look at. So divided by, if you divide this MB into y bar by I, you get that bending moment, or sorry, bending stress. So this y bar here is nothing but centroid. Centroid means center of area, and center of area from which direction? By the way, this is the area, right? This is your t, and this is twice t. So it will be the center here. Half from here to here is what? T by 2, right? From here to here is what? T T. Okay, so your center of the area is located at T from, if you take vertical direction, so this is twice T, so this will be at T, half position. This is T, so this will be T by 2. But which direction we take? Y bar will take, will be equal to only one midpoint from any side, you can say, or from any direction, either vertically or horizontally. That means y bar will either be equal to T by 2 or T. Understood? So which one will take? That depends upon which you can say about or you can say previous, that depends upon the previous orientation of your area and the current orientation of the area. Okay, you can just think like this is the area first initially, and after the rotation it has come here. You can understand this, na? This is the area, this was the area first, okay, like this, and then it has rotated in this manner. Understood? Okay, now this is what is your rotation, and then you have to take this side, okay, this side or vertical side. Okay, if your area has rotated in this manner, how to like this, let's say, okay, that means in this manner. Okay, previous area was like this, now it has rotated in this direction, okay, or in this direction, not like this or this. Okay, then you have to take what this as a center, because your bending has taken place like this. So all these concepts actually you should grasp yourself. Okay, one thing, that this video, every video will be limited to 20 or so nearby minutes. Okay, so let's continue. Okay, so this thing, now y bar will take half of this distance, that is the centroidal distance. So this is T. Okay, T, because T is your downward direction. T is your y bar is equal to T. Okay, bending moment you have to find out. Okay, what is the bending moment? That is force into perpendicular distance only. Okay, so up to which perpendicular distance we have to find force, and here this is the axis, or this is called neutral axis. Here there is no stress, so from point of application of force up to the distance of neutral axis is what your bending moment here. Okay, so that distance is given to you. Okay, so 10. Alright, not up to this axis, actually it has started bending at this point. Okay, here like this, right? So the force multiplied by distance from the center up to the top surface, where maximum tension will take place. Here compression will take place, here net tension will take place. Actually ultimately you have to take the maximum bending stress. Bending stress will occur everywhere. If I go to detail in this, then bending stress will occur at each and every layer of your frame. Okay, and the maximum will be at the top portion. So maximum, if you consider bending moment at any point in the neutral axis, will also get a bending moment. In the bottom portion also will get a bending moment. Here also anywhere, but the maximum if you consider, because everywhere since we are preventing the failure, we have to consider maximum bending moment, and that's why maximum bending moment will occur at the top surface. Okay, or maximum bending stress will occur at the top surface. That's why we need the distance between point of application of force to the top surface. Okay, that is given here in a question 10, from point of application to the top surface of your offset link. Okay, so now last thing, moment of inertia. Okay, so moment of inertia, I told you, for rectangular section with this dimension, okay, as B, and this dimension as H, if this cross section has rotated about an axis which is at B, okay, or parallel to B, that means look at this. Okay, this let's draw it like this. So this is P here, P, okay, and this is H. If the whole your area has rotated about B and it has come to some position here, rotated like this, you understand? initially it was this here, and it has rotated in any direction but about P, or any axis here somewhere. Let's draw it again. So here, any axis which is here, so it has rotated to a new position. Understood this? Okay, any axis, or maybe the axis is not even touching the surface, that may be somewhere here also. Understood? Then about the axis, it may rotate either in this direction or this direction, so it will come here. Understood? Or if you go that side, it has come here. So all these axes which are parallel to you have to look at the initial position of your area and final position of the area, and look at you have to imagine an axis about which the area has rotated. Okay, compare between this area here and the final area which has bent in any direction, either in this direction or this direction. So if you compare this one, this is what, T. Okay, I mean this red colored one I am taking. So this one is T, this much is T, this much is twice T. Okay, so initially it was vertical exactly. After rotation, it has rotated like this. So this is T and this is twice T. So you can say any axis which is parallel to T, okay, that is the axis of rotation for this your for the area, right? So for this case V and H, okay, when the axis of rotation is parallel to the dimension, that dimension, see, formula is 1/12 BH cube. Now you always remember which one will have the cube sign. Sometimes it is 1/12 HB cube. Always the dimension which is parallel to the axis of rotation, that will not have the cube sign. Actually, this is a derivation. There is a derivation for this. Okay, all these things are available in mechanics. So you see, when this area rotates like this, when the axis is at parallel to this axis, parallel to this dimension, or which is at the dimension itself, then this will be 1/12 BH cube. Here you see, look at this. This area was, I mean, T has not changed. Okay, only the orientation has changed along twice T, like this. So here it is like T, and this is twice T. Okay, so this will be 1/12 T into twice T cube, right? Okay, if the whole thing has, suppose, bent in this manner, if it has bent in this manner, see, I am just explaining the concept. This is, so you must understand all this to solve numericals. Okay, so imagine this, I mean, how to, can you imagine? Okay, I mean, oh sorry, okay, so initially it was, this is the C clamp. Okay, so it has bent in this manner. Previously it was bending like this. Okay, like this. Okay, so now you can say this is the C clamp, right? So you can imagine, here we are pulling, here we are pulling, here we are pulling. So it has bent either in this direction or in the opposite direction, in this manner. Understood? So then look at the area. This is the area, right? Initial area and final area will be here somewhere. Now you can write down I equal to what? 1/12. So this is 1/12. You see, this is T and this is twice T. Okay, so 1/12. This will be, now see, this area, this axis, we can say initially the area was like this, and after rotation the area has gone here somewhere. Okay, you see, so the axis of rotation will be like this, vertical, isn't it? And the side which is twice T, which is parallel to that axis, will not have that cube sign. I mean, sorry, cube, the power above it. So it will be T cube into twice T in this case. Okay, don't make any mistakes in this thing. Okay, because you will solve problems, okay, based on bending. Now let's go to the problem. It's about to be okay. So yeah, quickly I'll tell you. So look at this. P force is given. This is ultimate tensile strength is given because this is the brittle material. So Fg 300 is given to you. So it's a brittle material. So this is the failure strength. Okay, factor of safety is given. So permissible tensile strength or permissible maximum strength that you have to see. If you apply 300, anyhow combination of tension and bending, if it crosses 300, then it will fail. Okay, so it must be below that. So 300 by 3, factor of safety is given as 3. So this is your 100. Actually this is permissible maximum stress for the link, you can say. Okay, which is a combination of bending plus tension. Okay, now cross section of the link is subject to tension and bending. This I have already explained to you. This is how tensile failure will take place. This is how bending will take place. Okay, now see, total stress, permissible stress will be the combination of tensile stress plus bending stress. Tensile stress is force P by A equal to bending stress is sigma mb into y by I. Okay, simple thing. Now force is what? Force is given to you 25. Okay, 25. You put the force 25 here. Okay, area is 2t into t, that is the cross section area. See, if it fails like this, tensile failure takes place, then area will be what? This 2 t into t. Okay, that is the area of separation. Okay, and see 25. So this is t into that. And I told you that bending moment is what? One thing I missed actually. Yeah, so maximum bending moment actually will occur. Actually that's a mistake I made. So maximum, look at this. Actually maximum bending stress will occur at the top portion here, and minimum bending stress will occur at the neutral axis, but maximum bending moment is possible along the neutral axis only. Okay, not at the top. That thing is actually true for bending stress. Bending stress is maximum here at the top portion because it is extending the farthest. Okay, farthest extension is possible here. Okay, so I think I should actually continue in the next video because time is up and the video will stop unnecessarily. Okay, I'll just continue this problem in the coming video. Thank you.